And they destroy
I'm more experienced.
I don't know. I'm thinking like, how many games?
Okay. We ended on Friday with compound interest. Like how much money you're gonna have if it's compounded monthly, how much money you're gonna have if it's compounded quarterly. Okay. So it looks like that. Now all right, this isn't like a direct compound. Let's say compound quarterly, let's say compound monthly, but it will become a compound interest problem. Okay? If you read that, it's saying it's increasing at a rate of 4.5% per year. That basically means we're going to figure this out every year, which means n equals 1. If n equals 1, what's going to happen to that messy equation? It's going to simplify a little bit. So take a look at here. If I let n equal 1, it just becomes p times 1 plus r to the t power. Okay, so it just makes life a little bit easier. That's what we're going to use for anything that is growing at a rate, at any decimal rate per year. So now we just put everything in. So instead of having like money in the bank, you have the price of your house. So it's $128,000. That is P. 1 plus 0.045. Actually, I don't need to divide it by anything. So just 1 plus 0.045. In this case here, we're going to have 12 years from 2000 to 2012. Just type it in. Okay? Type it in and see what you get. Now, since we're not dealing like with money in the bank, you can go to the nearest dollar. It's fine. You don't need to go to the cent. You're not going to put your house on the market for, $100,000.99. So just the nearest whole number is fine. All right, Phoenix, let me know what you get.
$217,072.
All right, $217,072. Okay, so it's increased in value in 12 years from $128,000 to $217,000. Okay, for that. Now, if you paid attention here lately, our house values increasing or decreasing? Yeah, they're increasing. They're increasing at a probably even bigger than a 4.5% rate. Okay, so they're going big. Houses usually increase in value. Cars typically decrease in value. Unless there's a classic car or it's a collector's model. But if you go buy a Ford Focus, in 5 years it's not going to be worth more than what you paid for. Okay. Maybe, but yeah, in some cases, because with production issues, cars are worth more for that. But so a typical car, if you buy it, it's going to depreciate. Now there are situations where that may not be true. I know they were looking for used cars recently, and some people were actually selling them back to dealers for more than what they bought them for. Okay. But let's just take a look at a typical situation. So if it depreciates, here's what it's going to be. Per year, it's going to be 1 minus r to the t power. Anything that appreciates in value, you're going to add the interest rate or add the rate. Depreciates, you're going to subtract the rate. Okay, so for this one, we're going to figure out what its value is going to be in 5 years. So it's going to be 15,000. 1 minus 0.09 to the 5th power. Again, nearest whole dollar is fine. Josiah, let me know what you get.
9,360.
9,360. So it was originally worth 15,000. Now it's worth about 9,300, 9,400. Okay, for that one. So it lost a little bit of value. All right, now this last example is kind of going backwards. So instead of figuring out, so all right, if I start with 10,000, how much am I going to end with? We're going to figure out, all right, I want to end with $50,000. How much do I have to start with to end up with that amount? Okay, so your grandma wants to give you $50,000 for college when you turn 18. So it's going to be her big gift to you. How much would she have needed to invest when you were born if she's getting 8% interest compounded quarterly? Okay, so now this is a compound interest problem. Okay, so A equals P times 1 plus R over N to the NT power. So we got to go back to this. It's not, since it's compounded quarterly, N is not 1. N is 4. R is 0.08. We want the final amount. So that's going to be 50,000 here for A. We are looking for the principal. How much I start with? I got 1 plus 0.08 divided by 4 to the 4 times 18 power, because it's going to take 18 years for that to grow. Do not round off within the problem. You got to wait to the very end. Okay, you got to wait to the very end. Now you can type this whole thing in and you can divide, because I'm going to have to divide by 1 plus 0.08 divided by 4. 4 times 18 is 72. I'm just going to make that 72. For that. Now you can figure out what that is. You can do 1 plus 0.08 divided by 4 to the 72nd power. Okay, and then you can take 50,000 divided by that, but you're going to have to hit divided by second answer. Now, I'm hoping most of you know how to use that second answer button. Okay, it takes whatever's in there, doesn't round it off. Okay, it gives you that. You could type that whole thing in one. You just got to watch parentheses. So I got what, 12,000. I'm just going to round it nearest dollar. 12,016. Okay, so that's what she would have to start with with those conditions to end up with 50,000. Okay, in the end. All right, compounding interest. We can compound it quarterly, we can compound it monthly, we can compound it daily. There's really no limits on what you can compound it. Okay, so if I can compound it every day, I can compound it every hour, I can compound it every minute, I can compound it every second. Each time is going to go up a little bit. Now to demonstrate it, it's really easy to take the value of $1 at 100% interest. So if you think about this, A equals P times 1 plus R over N to the NT power. And we're going to do it for 1 year. 1 year. So what that becomes, if it's $1, my P is 1, so that really goes away. R is 100%. Well, 100% as a decimal is what? 1. And this is, I'm doing it for 1 year. This just becomes 1 plus 1 over N to the N power. Okay, T is 1. 100% becomes 1. Now, if we do it one time, you get $2. If we do it 2 times, I get $2.25. And if I do it quarterly, I get $2.44. Okay, now I'm going to want you to round it to 6 decimal places, even though I know we normally round it to 2. But for all these, round it to 6 decimal places. So let's take a look. Everybody kind of do these 3, and then we'll split them up because we know what N should be. It should be 12. Weekly should be 52. And daily is 365. All right, so do those 3. Check them with whoever you're sitting by. Make sure you're good. It's 6 decimal places. 6 decimal places. Okay, and it's going to be 1 plus 1 over 12 to the 12 Kate, what do you got for monthly?
For the final one?
Yep.
2.613035.
Okay, 2.613035. Okay, Alec, you got weekly?
2.69259.
Say that again. 2.692.
59.
Should be six. I want 6 decimal places.
Oh, 6.
So 596.
Yeah.
All right, we agree with that. Sam, you agree?
Mm-hmm.
All right, Marissa, what do you got for daily?
2.714567.
2 point. I messed something up. 2.714567. All right. So is it increasing each time? Yeah, but what else has happened? It's increasing at what I would call a decreasing rate. Okay, so each time it's getting a little bit bigger, but not at the same increment. So theoretically, you might think, well, this thing should go to infinity if I keep doing bigger and bigger and bigger numbers. All right, so let's just take a look at what's going to happen. So from here, we want to do hourly, every minute, every second. So hourly, we just take 365 times 24. What is that? 8,700 and something. 365 times 24. Okay, 8760. So I get 8760. Take 8760 to get every minute times 60. I get 525,600. And now every second of every day, I'm going to get some interest. 31,536,000. 31,500,000. Okay, now let's go split that up between the, if you're sitting by sides, one of you do one, one of you do the other, and then both of you do one. Just double check it. See what you get. Kind of make life a little bit easier here. And 6 decimal places. All right, Alexis or Maddie, hourly. Which one of you?
I did hourly. It was 2.718126.
8126. All right, every minute, Vincent or Matt.
2.718279.
8279. Okay, and every second. Okay, let's see. Back to there, Emma or Avery.
2.718282.
All right, this thing at daily got to 2.71, and we still see 2.71 for hourly, minute, and second. But is it still increasing though? Yeah, if you go out far enough, it is getting bigger. So this is 714567, and this goes to 8126. Then it goes to 8279 and 8282. But it's getting incrementally bigger. It will level off. It will get to a certain point. It will not go to infinity. Okay, it will level off at the number E. The number E, which is, who knows who's named after? Who's in your academic challenge? Euler, Leonard Euler. So this is named after Leonard Euler, Euler, but you spell it like the word oil. So Leonard Euler. Like we're talking like 1700s, he comes up with this stuff. Like it's crazy. So the limit as n goes to infinity, as it gets bigger and bigger and bigger and bigger, is going to go to this number e. It's like pi. Okay, never repeats, never terminates. Okay, never ends. So it's the same concept as pi. This value, and it gets used in a lot of different scenarios as you move further and further up in the math world. Okay, it's on your calculator as well in 2 spots. It's got 2 spots. It's so popular. If you look at the division key, second, if you hit E, you'll see this. It appears to repeat, but that's just because of the round off value. It does not actually repeat for that. And then the other place is on the left-hand side, the third button up, where it says ln. If you hit second, it just gives e to a power. So if you want to do e squared, okay, if you want to do e to the negative second, okay, for that one, it'll work. But that is the situation as this gets n value gets bigger and bigger and bigger. So now in terms of money, we have no limit on what we can compound. So we can do it every second, we can do it every half second, we can do it every 10th of a second, every 100th of a second. Well, in theory, we're just going to do it continuously. We're not going to take a break. Our formula becomes this. A equals P times E to the RT. Pert used to be a shampoo. Is it still out there? No. Back in the day, Pert Plus. So that is the case. R is your interest rate, T is your time in years. Only for continuous compounding does that work. Okay, only for continuous compounding. So if you look at that last example there on the bottom, okay, it says find the amount in an account if $10,000 is invested at 6% interest for 20 years and the interest is compounded continuously. So you got to be told that. You got to be told that in order to use this formula. So since it's compounded continuously, we'll use A equals P times E to the RT. This is the absolute best scenario. Like we said, the more times you compound it, the better. Cannot do better than compounding continuously. So we plug in $10,000. E to the 0.06 times 20. And just type that in your calculator. Or let me know what you get when you're done. To the nearest penny. Since we're dealing with like money. Got it?
33,201.16.
0.16 or 0.17 if you round it.
Oh yeah, 1 cent. Yeah, 1 cent.
0.7. All right. I want that penny. Don't take my penny from me. So $33,201. So it went from $10,000 in 20 years to $33,000. Okay, so it gained $23,000 of interest. If it's compounded continuously at 6%. Now E is a constant. So flip it over. We can graph it. We can do anything. We would do with any other constant as well. So let's take a look here at this case here. So e to the x power. And just beside there, I'm just going to do a real quick XY chart so it makes a little more sense. From -2 to -1, 0, 1, and 2. Probably nearest 10th or nearest 100th for that. So if you look at e to the -2nd, I'm going to make that 0.14. So that's 0.14. E to the -1st. What do I get there? I get 0.37. Ooh, I can do this one. What's e to the 0 power? 1. Anything to the 0 power is 1. All right, figure out what e to the 1st power and then e to the 2nd power is. e to the first power, if I round it, 2.72, right? 2.72. And I don't remember this one. E squared. 7.39. Okay. So those are these values right here. It still has a horizontal asymptote of y equals 0. Okay, it's never going to go below 0. Because you're taking a number to a power, it's always going to be positive. Okay, it's just going to get closer and closer and closer to 0. All right, let's take a look at a couple of those graphs. First one, e to the x minus 2 minus 3. Okay, see what we come up with for that one. We do want to list the domain. We do want to list the range. Now I'm going to use my transformations to figure that out. So I'm just going to graph the original one, e to the x, which was at like 0.1, pretty close to 0.4, 0, 1, 1, 2.7, and then 2, 7.4. All right, we've still got our high school RV. Ella, horizontal shifts. What do you think? Flip it around, not left. Right 2, because every time it's a minus, you're going to actually do the opposite. So make it right 2. And what else we got going on in this problem? We go right 2. Kate, what else we got going on?
Down 3.
Down 3. All right, so take each point, go right 2, go down 3. Okay. Also think about your domain, think about your range, think about your horizontal asymptote. So now, right 2, down 3. Okay, and then I'll take the point at 1, 2.7, go right 2, down 3, go right 2, down 3, right 2, down 3, right 2, down 3. Hey, do draw in your horizontal asymptote if it's not at the origin or at y equals 0. It's actually now going to be at y equals negative 3. Ooh, I didn't draw mine very straight. There we go. So there you go. Domain, all real numbers. Range, negative 3 to infinity. Horizontal asymptote, y equals negative 3. So domain, negative infinity to infinity. Range, negative 3 to infinity. And then horizontal asymptote, y equals negative 3. Okay, for that. All right, once you get done with that one, look at the one on the right. That equation. Think about what's happening, what transformations are happening. I'll go over them here in a second. If you think you're good, keep moving forward. If you just want to wait, that's fine as well. Think about like high school RV. With horizontal shifts, stretching the press, flexions, moving it up. And I'm going to graph the original graph on here again, just so I have it. Right. So what do you have? What do you have down?
I said left 3 reflects y and up 1.
Left 3. Since it has a negative there, reflect in the y-axis, and then it's going to go up 1. Agreed. Make it left 3 because that's the same as negative x plus 3. Okay, so it's the same here. The plus 3 moves it left 3. The negative in front of the x is going to reflect it over the y-axis, and then you go up 1. That's going to move your horizontal asymptote. I'm going to actually just put that in there now, just kind of as a reference point. It's usually at y equals 0. It will now be at y equals 1 when we go to do this. All right, so see what you come up with for your new graph. All right, let me see here. Left 3, so I go 1, 2, 3, and then we'll reflect over. So I'm actually going to be up above the graph a little bit there for my first point. I go left 3, and when I reflect, I go 2. I go up 1 to 3.7. At 0, 1, I go left 3, reflect to positive 3, up 1. Left 3, reflect to negative 4. Up 1, and then I'll have my other point there. Okay. It will keep sliding to the left, so it will be negative infinity to infinity on domain. Range will be negative 1 to infinity. Horizontal asymptote at y equals 1. So domain, still negative infinity to infinity. Range, negative 1 to infinity, and then our horizontal asymptote again is y equals 1. All right, so we got E as a constant, just like pi, irrational number. This also comes up into situations with exponential growth or exponential decay. Now there's your typical formula. A of t equals a sub 0 e to the kt. Now you may not recognize it, but this is actually the exact same thing that we use for continuous compounding. Okay, they just use different variables. Okay, instead of p, they use a sub 0, the original amount. And then instead of r, they use a growth rate. If it's positive, it's growing. If it's negative, it's decaying. So anything with exponential growth or decay, we can use this formula. All right, that example down here, the population of a town has been growing exponentially. You have to be told that. Okay, to use this. Since 2000. The town had 24,500 residents in 2000, and the annual rate of growth has been 1.25%. Determine the population in 2020. So we're going to use this A of t equals a sub 0 e to the kt. All right, k is 1.25% as a decimal. Make sure you make that 0.0125. All right, see what you come up with. Round to the nearest whole number since we're dealing with people and that money. So my A sub 0, that's your original amount, 24,500 people. E to the 0.0125 times 20 years. That's the time. You can type this all in at once, 24,500. I'm going to use this E on that left-hand side because it automatically has a power. Not that you couldn't use it over there. I really don't know why they have two. 0.0125 times 20. And let's see what we get there. 31,459 people. So 31,459. Okay, for that. All right, a lot in that section. Okay, compound interest. We got XE. Now I didn't do my math lab because it didn't give me some of the problems that I wanted, so this is going to be out of the book. I know that other math lab is due tomorrow. I actually haven't looked to see who's turned it in or hasn't, but this will be due then Wednesday if you need the extra time. If you get them both done, great. I mean, actually, I'll go through tomorrow and see who has it done, but you won't lose any points if it's not. I got to go make a quick copy for Matt, and then I will be right back.
So we don't have to do the one
What's that?
We don't have to do the my math lab on Friday.
That's due tomorrow.
Oh, it is. Yeah.
Yeah, the My Math Lab is due tomorrow. So yes, that does need to be done.